Hello, everyone, and welcome to PyData Global 2025. We are so excited to have you join us. Feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab, and we'll address them at the end of the session if we have enough time. Now, it's my absolute pleasure to introduce Robin Troesch, who has a talk entitled Building a Lightweight Feature Store for Electricity Grid Forecast with Polars. Please give it up for Robin.
Hello, everyone. Thanks for joining and thanks for your introduction. So a little word about myself before starting. So I'm Robin. I work at Electricity Maps since 2022 as a data engineer, originally in the data platform team and now in the grid forecast team. And today we're going to talk about one of my main missions currently, which is to make sure that our models get all the features that they need to produce forecast and distributing forecast to a customer. And we're going to focus really on the first part of that journey. So we're going to dive into first, what is the forecasting problem that we have at Electricity Maps, why we needed a feature store, then breaking down how our feature store works and sharing a few learnings along the way of how we built it. So let's start with forecasting at Electricity Maps. And for that, I'm going to first start with a quick introduction to what Electricity Maps is. So Electricity Maps maintains a comprehensive database of the world's electricity grid data. And using this massive data set, we started forecasting electricity grid signals, which then our customers can use to those forecasts to plan their electricity consumption. For instance, to optimize the electricity consumption when the grid is powered by clean energy, or reduce their workloads at a time where there is a peak demand on the grid, therefore smoothing the energy transition. In terms of scale, we cover the entire world, which we split in more than 190 zones, as defined by the grid operators all around the world, as well as the interconnectors between the zones. And for forecasting, we forecast all the different production modes, so like wind, coal, solar, and all the modes that you can imagine, plus other signals such as import and exports, the electricity prices, the load, the live carbon intensity, and the renewable energy percentage even. And even more signals are added on a weekly basis to our platform. And this is what our forecast can look like for a specific zone. Here, for instance, we have a power breakdown per production mode for a zone. And as you can see, the forecast problem at Electricity Maps is essentially a time series forecasting problem, where we issue forecasts for different grid signals up to 3 days in the future at a very low granularity. It depends a bit on the grid, but most grids now in Europe would be, for example, at 15-minute resolution. Some other grids are at 5-minute resolution, or other grids are at an hourly resolution. We continuously issue forecasts updating our previous predictions with newly available information. And this is one of our fundamental concepts behind our forecasting system, because the issue is that our features that we will use will need to know what information was available to us at which time. This is essential to train a model. This is why we are dealing with stateful time series features, which are two-dimensional time features. We call those two-dimension target time, when is this prediction for, and the reference time, when was this prediction made. Let's break down an example. We use a weather forecast for the 3rd of December at 1 in the afternoon. 48 hours before, the forecast says it's going to snow. 24 hours later, when we have more recent measurements, they publish a new forecast saying that on this specific hours, there will actually be sun. And this is happening for all of our features. This is also happening for features related to the grid, where grid operators will publish, for example, a first estimation or forecast of the load or the consumption on the grid. before revisiting those numbers several times throughout the day. And certain features will even be only published on short notice. So you won't have them to make long-term forecast. You will only have them to make short-term forecast. So it's all about the time of when you will make those forecasts that will matter, and we need to organize those features in such a manner that they reflect this complexity. So now that I set the scene a bit for our forecast problem, why did we even need a feature store? And why am I talking about this? So to understand this, let's look a bit back at what we had initially at Electricity Maps. At Electricity Maps, we initially had a very, very simple system to generate features. We just generated them on the fly. We had some code that we called feature inputs, which were essentially a collection of collector classes responsible for getting the input that we need to generate features. This could be by connecting to the weather provider or querying on internal database for grid data. And then we had some classes that we called feature generator that were responsible for transforming those inputs into features. Simple. This enabled us to do fast iterations because we could just update the feature generation code and we had new features on the fly. Those features were then used in our training pipeline to generate features for training. We used Apache Beam to scale the whole feature generation process across several zones. So the problem was parallelized across different zones or interconnectors, depending on what we want to model. And we use then the feature generators in another mode to which was just plain Python to generate features for inference. So using the train model, we then use the same feature generator to generate features and make out of those predictions, which we could then forward to our customers. And at first, this worked quite well. This enabled us to quickly bootstrap our forecasting setup. But as the team grew and ramped up our forecast offering, we started seeing some issues. The on-the-fly computation meant that we needed to wait every time to materialize features, pay for them every time, and it was really hard to share features between users. Things got even more ugly when we started to scale our forecast from training, for example, from a monthly data to yearly data and increasing the forecast horizons to from 24 hours to 96 hours ahead, so up to 4 days ahead. Generating this large amount of features for large zones like California became impossible. This is, a quick view from our cloud provider when we try to compute very large features of the grid plus the weather at a maximum resolution in California. This started becoming quite a bottleneck for us. We were generating, in the end, very large Parquet files of 30 gigabytes for experiments, which were just impossible to open on a computer without hundreds of gigabytes of RAM attached to it. We encountered frequent memory problems. Experimenting with those with new features also became very hard because combining features was not a straightforward task. Features had each their own resolution and frequency, so we spent a lot of efforts writing code to try to bind them together, and features were also tightly coupled together, so we ended up writing a class for every combination of feature that we wanted, leading to a class explosion. Like, we wrote a class basically for every combination, and that became quite some trouble to manage. So just to recap, essentially we were dealing with big limiting factors in our ability to scale forecast. Experimentation was slow. We were burning through our cloud costs, and we were frustrated because it required complex memory management to get things through in our current setup. So this was no longer sustainable for us. So we came to the idea of decoupling feature generation and have them already ready for us. And this is the idea behind our feature store. And then we came up a bit with a list of requirements from our previous experience of what we wanted from this feature store, which was, for example, we wanted the features to be ready in a matter of seconds for inference and debugging. Like as a data scientist, I need to visualize features super fast. I made a change, I want features in 5 seconds tops. Getting features for training should come in a reasonable time. This would be less than 10 minutes usually. This is a bit more acceptable to wait because we don't do training so regularly. We do it once per week or once per month, and then we can afford to wait a bit longer. Combination of features should be just easy and convenient. It should be a seamless approach. And finally, this came a requirement from electricity maths history. We wanted to keep models very simple, and this meant that the model will have to see all the features for training at some point. We trained very simple linear models, and that meant that we needed to materialize the features in memory, all the features at some point. So this was still a bit of a requirement, but we would need to shift a bit around the whole feature process so that we don't explode in memory too early on in the pipeline. And we had a guiding principle, which was also to keep it simple and maintainable. So now let's take a look at how we built this. So this is a bit of a general overview of how we decided to build our feature store. In general, we kept some of the feature generation process. You might recognize this on the left part of the panel, but we simplified it. No more feature combination at this level. We simply made a pipeline that for each feature input was able to generate one or more feature frame for a given ref time. For instance, the weather data could be used to generate features at several resolutions, and we made sure that all of those tasks of generation were independent of each other, were between zone and also ref time. This means that we ended up still with an embarrassingly parallel problem that was easy to make it scale, and that we still decided to go with Apache Beam in Python that we knew how to use, and just were able to scale it much better because we were dealing with very low, very simple problems to solve in parallel. And because we split the problem into small chunks for each entity that we have in our system and for each ref time, we are able to generate only small chunks of features. And from now on, all the feature generation will be handled the same way, whether it is for training or inference, and all of this will be done in the feature generation pipeline. Those small chunks of features are then exported to our storage, which is just a Google Cloud storage, a cloud bucket organized into a hierarchy of entity. So this can be like different production or consumption zones or interconnectors. Then the next level would be the feature generators that are available at this. So for example, all the weather points that we have for this zone and a certain resolution, or the hourly grid data, or like cyclical features like the working days or stuff like this for specific zones. And then we export all of this or like for each ref time, we will write a Parquet file that we will just store this in this bucket. And we will have a client written in Polars that allows us to query this bucket. So that's the overall idea. And now let's dive into the querying logic. So let's go through a query together. The user will start by saying that they want features for a specific entity that they want to model. This could be a zone, an exchange, or other entities that we have. The start and end date for those features, the maximum lead time, and that means that for each target time that will be in the feature frame, how much in the future do we get features. So we will have, for example, if we specify a lead time, maximum lead time of 96 hours in the future, we would get for each target time 96 versions of it, seeing all the different features that became available through time. And finally, the resolution of the target times that we want. So for example, is it 5 minutes, 15 minutes, or an hour? And finally, the user would specify or declare a feature set, which is a recipe for the feature that the user wants. And let's dive into this recipe. So they would start by choosing the feature generator that produced those features. In this case, the user selected, for example, grid state features and exchange state features. So you can see this from the two generator that they selected. They could also select a bit more granular, like saying that in those categories they want only specific column regexes. And then they would also specify the relationship between the features that they are getting and the entity that they are modeling. So for example, in this case, like the user would like the grid state features of the entity itself that it is trying to model. And for the exchange features, they want the features of all the interconnectors that are connected to this entity. And this is specified by the entity relation, and that maps like how do the features relate to the entity that we are trying to model. And now the feature store client will look for all the table references inside the feature store. On average, here we query around 15 different tables for a dedicated feature set. That's a bit like our best feature sets that we built so far, or the most useful to us. One essential part of the query is made possible by Polars, is that we will do this whole process lazy. This is done through the scan parquet method of Polars, where we'll for each table specify the path, and this will give us a lazy reference of the table that we are trying to model. And this means that at this stage we do not load everything into memory. And this will allow us to smoothen out the memory peaks. The output of this process is then a list of lazy frames of all the tables that we need to generate features for the user. And now let's move to the second part of the query process. Remember when I told you about the two-dimensional time problem, target time and ref time? This is what we're going to deal with now. So it's an essential problem in our data sets that we have features that each have their own update frequency and resolution and even maximum look ahead. Let's look at an example to explain it better. We have weather data that is updated every 6 hours with a 1 hour resolution, and grid data that gets updated every hour with a 30-minute resolution. To be able to train a model that can produce forecasts for any target time in the future, it will need to see what is available in each situation. And what does that mean? That means like what is available in each case. So we will need for the training a feature frame that has all the possible lead times that we might want to do forecasts for at a single resolution. So this means that for some of the features, we will downsample to a lower common resolution. For instance, the weather data will be downsampled here to half an hour resolution here. And for the weather data, we will also even backpropagate the last observation to lead times that are closer to us, because this observation is still valid and we want to have it at all the different lead times. And in our feature store, we decided to make our lives easier by separating concerns. Each feature generator will store every entity the features in their own native resolution, and we kind of like go away from the responsibility of combining features at the feature generator level and delegate that to the feature store client. This means that there's a storage, like each feature is stored at their native resolution. We do not try to guess in advance what the user will request or something. We all delegate this to the feature store client, greatly simplifying our problem by trying just to solve the right problem at the right time. It didn't make sense for us to try to solve the problem of aligning the resolution already when we are generating the features. The features need to be available, and then we go to a common resolution later on. And then this is how it will look like. The feature store client will first align on the requested target time resolution by downsampling using a join on expected target time and lead time. And we do this on an expected target time and lead time data frame that we just generate lazily. And why do we do a join and not a downsample operation? This is simply because the join operation can be performed lazy. As to the downsampling operation, this cannot be done lazily, and we want to keep being in the lazy framework as long as possible, so that we only materialize in memory what is needed, and Polars can optimize the query plan for us. And then we do another second lazy operation, which is that we will backpropagate the last observation to all the lead time, again using a join, this time a join as of, to stay lazy. And now we bind all this to the process to the query. Those time alignment operations are done on each individual table lazily, and we stay lazy at this point. We then sort each frame and concatenate them still lazy. We do a sort so that we can just simply merge vertically without any other checks on the frame. And then we have the final result, which is a unique lazy frame. We're still lazy at this point of all the requested features merged together. And then when the user is ready to consume this frame, when they have, I don't know, already enough memory that is in the machine or something, or when they're ready to start the training, then they will call the collect method of Polars, which will materialize an optimized frame with an optimized query plan, and this greatly reduced the number of memory spikes that we're seeing, reducing a lot, completely removing all the memory bottlenecks that we're experiencing before. And now let's quickly talk about how we optimized our query for our inference use case, which is a thing that will run every day, every hour, even more than every hour, every day. So our first approach on storing Parquet files, we run our inference engine every hour. So we thought, okay, let's just do hourly Parquet files for our features. And if we do the math, that means that when we do the training, for instance, like we need to load 360 days times 24 hours, so 8,000 files. And then we had typically 15 entities or tables to query. That means more than 100,000 files. And that resulted in Polars being quite slow at partition pruning, probably limited a bit by the ability of GCS to just list all the files, because it was starting to paginate results. And like then Polars couldn't efficiently prune our files, and basically we ended up in a situation where we were trying to get or scan a lot of very small files, which was completely inefficient. So we tried something else, and we started to compact our feature files together. And we decided to introduce some compaction here to regroup the features for a same data forecast within a single Parquet file to get a more optimal file size. From what we found online, the optimal file size for Parquet files would be around 50 to 100 megabytes, according to our calculations. And this, we just did it using Apache, still Apache Beam, where we introduced the last step of our pipeline, which would just regroup per reference times, on the same day the features together. So we might have several observations of the same features inside the same Parquet file for optimization purposes. And then when we do a bit the math on how many files does it mean, then we only scan around 8,000 files, and partition pruning can kick in. We have an efficient Parquet file size, and we end up with blazingly fast queries. And especially for our inference use case, this goes super fast because it's only a couple of files to scan. And we just need to add on our scan Parquet file. We added just a filter, still lazy. By enabling the Hive partitioning, Polars was able then to know which partitions can it keep or which partition should it remove based on this ref time day. We have a way to just infer that okay, I want to make predictions for between this ref time and this ref time, or the start and end time. This is approximately the partitions that I want to load. And this is why we introduced this new filter. So yeah, that's almost it. I'm going to quickly recap with some of the learnings that we had. So compaction was key. If you try to scan too many small files, your performance will be degraded. We also thought about what if we delegated this compaction to Apache Beam or Delta Lake, which is supported by Polars, and they do this compaction and will find another compaction ratio that is more optimal. And the reason we decided to not do this was that we wanted to keep things quite simple. We also didn't want to go too much into distributed. You could argue that we already did with Apache Beam, but we didn't feel like going fully distributed with something like Iceberg and Delta Lake. We still wanted to be able to run things on a single node. So we were, okay, let's keep it quite simple. And also for a data scientist, like if I go to the feature store and I look at a Parquet file, I can immediately read and understand what is in there. But it could be also an alternative to go to one of those solutions like Iceberg or Delta Lake straight directly. Use the lazy API of Polars smartly. It greatly reduced our memory spikes that we were experiencing through our whole process, and this enabled us to run complex operation on large datasets in just a single worker. So we don't have any huge memory spikes because Polars generates for us an optimized query plan, and then it just gets the file that we need, and we can run this in fairly small workers instead of behemoth machines that we needed to get before. And finally, one of our most important learning was also to break down our problems into several steps. Think of what is the only responsibility each component needs to do. Don't try to solve our responsibilities all together. And where we landed is that we're able to run the whole get features process for a model on a single node, and that could be on our computers. And we can get features for model for training under 2 minutes, basically. We are reading features for inference instantly. Testing out new combination of features is seamless. It's just declaration, and experimenting is again big pleasure. And we reduced our cloud cost for feature computation by 53% with a very minimal addition on cloud storage. And that will be it for me. So thank you for listening. I'm available on Discords afterwards because I think we might not have a time in this session for Q&A. So feel free to shoot your questions afterwards. Thank you all for listening.
All right. Thank you so much, Robin, for your talk. And thank you again, everyone, for joining us today. As Robin mentioned, if you do want to continue the discussion, feel free to use the lounge in the reception area. And also note that a recording of this session will be available shortly for rewatching. But yes, we will see you around for the rest of the conference today, and I hope you all have a great day. Thank you.
Thank you.